So last class we have discussed about the density of textile fibers and measurement of density of textile fibers by density gradient column. So we should proceed further. Our next topic of discussion is optical and X-ray diffraction studies. So session outcomes are students will be able to measure crystallinity of fiber, measure molecular orientation of crystalline phase of the fiber, and measure the size of the crystallites which are present in the fiber. So these are the three outcomes that you will be able to achieve after completion of this session successfully. So optical and X-ray diffraction studies. So diffraction, as you know, one of the important phenomena of light. Okay, you know there are few phenomena of light which are very important: reflection, refraction, diffraction, polarization, etc. So diffraction is one of the phenomena of light which has been successfully used for structural investigation of fiber. So now in this topic we shall understand how that diffraction phenomena of light as well as X-ray is successfully used to investigate the physical structure of the fiber. The scattering of fine beam of light is a diffraction phenomena that can be used to obtain information about the internal structure of polymer films or fiber. Internal structure, that is the physical structure. A polymeric crystal can be regarded as made up of layers of atoms, themselves regular in their two-dimensional plane, stacked regularly on top of each other. So you can see schematic diagram of the stacking of the polymeric structure. Okay, these black dots are the molecules, monomer molecules, and this line is, you can say, the polymer chain. Now in two-dimensional structure, this line represent a plane of polymer chain. Okay, now there are many planes. Okay, those planes are stacked inside the physical structure of the fiber. So if a X-ray, beam of X-ray is directed to a crystal, so if this is a crystal, it is strongly reflected whenever it strikes layer of atoms at an angle theta, such that n lambda equal to 2d sine theta. So it is a beam of X-ray. When the beam of X-ray will just incident on the crystal, there will be a reflection of the X-ray beam as shown here. Okay, if the incident angle is theta, then the reflection angle also will be theta. So this phenomena is actually obeyed by the Bragg's law in lambda equal to 2d sine theta, that is the Bragg's law that already you have studied in your school classes or in the first year of BTech engineering. So Bragg's law has been used to explain this phenomena of diffraction, where lambda is the wavelength of the X-ray, d is the distance between the plane, interplanar distance, which is shown here in this figure, and theta is the incident angle. Okay, or n is an integer. So now you can go through the Bragg's law detail from your school classes or junior classes, how the optical and X-ray diffraction can be explained by the Bragg's law. So now lambda is the wavelength either of the visible light, optical ray, or wavelength of the X-ray, which you have used for the structural investigation. Now angle varies inversely with the spacing. If you look on this formula, the angle theta is varies inversely with the spacing d. Okay, inversely proportional. So wide angle pattern give the information of closed spacing. That means if you use a larger value of theta, that will give you a smaller spacing, information of smaller spacing. So for measuring the smaller spacing, you need to use wide angle. Okay, because theta and the space d, they are inversely proportional from this formula. The smallest possible value of spacing 2d for which a solution can be obtained is the wavelength lambda. So lambda is the wavelength. The value of the lambda in nanometer, that will be the smallest possible spacing 2d. Okay, so you cannot be able to measure the space smaller than the dimension of lambda. Okay, that is important information or concept you must understand in this technique. Now, optical microscopy, even by using ultraviolet radiation, in optical microscopy generally visible light is used, okay, which is have a much larger wavelength or value of lambda. Even if one can use ultraviolet radiation, which is having the shorter wavelength, will therefore give information only on relatively coarse feature of the fiber structure. Okay, the spacing is greater than about 0.1 micrometer. So you cannot be able to measure the smaller dimension than 0.1 micrometer if you use even ultraviolet radiation for measuring the physical structure of fiber. Now, if you see inside the dimension of the various physical parameter of the fiber, as already I have discussed in my previous classes, the diameter of a yarn is around 0.5 millimeter. Okay, if this is a presentation of the yarn, the diameter of the yarn is 0.5 millimeter. So inside the yarn there are many filaments. So dimension of filament or diameter of the filament is about 25 micrometer. Okay, so in the filament there are interfibrillar domain, because the filaments are consist of fibrils. If it is a fibrillar structure, there are fibrils. In between the fibrils there will be the interfibrillar domain. Now I think all concept is clear to you about the fibrils and interfibrillar zones. Okay, now if you see inside of the fibril, a single fibril, inside a fibril, the dimension or diameter of the fibril is around 10 nanometer. Okay, so inside the fibril there are lamella. Okay, these are called lamella. Okay, or sometimes they are also called by micelle, and there are interlamellar domain or intermicellar domain. Okay, intermicellar domain or indeterminate matrix. If you can remember the theory of micellar theory or modified micelle theory, then you can understand what are the micelles and what are the intermicellar zone. Okay, there will be the lamella stacking. Okay, lamella stacking means if there is a folded configuration in the modified Keller's theory, there are folded configuration. Okay, there are folding of molecular chain. Then there will be the typical stacking. Okay, that is called lamellar stacking. So that all those features or configuration of the molecules are present inside a fibril. The fibril is having a diameter of 10 nanometer. So inside the fibril there are molecule chain, okay, or the polymer chain. The diameter of a polymer chain is about 0.5 nanometer. Now if you use only the visible light or the UV radiation, okay, for the diffraction studies, okay, then only you can be able to measure the diameter the diameter of 0.1 micrometer. You cannot go below that. You cannot be able to measure a dimension less than 0.1 micrometer due to the limitation of the wavelength lambda, okay, of the UV radiation. So if the dimension is 0.1 micrometer, you cannot be able to measure what is inside the fibril. You cannot be able to measure the dimension of lamella or micelle, okay, whatever the molecular orientation or molecular order which are present inside a single fibril. But if you can be able to measure what is there inside a filament, the coarse feature, defects in the filament, okay, long range order, that can be measured by, maybe that can be measured by the optical light or ultraviolet radiation. So what is the approach? Then you need to go for the radiation which is having much shorter wavelength. Okay, so you need to go for the X-ray, okay, which is having a much shorter wavelength. So X-ray diffraction is the most important tool for the study of fiber structure, okay, which is having a dimension of 0.1 to 0.5 nanometer. Now you are coming in the nanometer zone. So you can see what is there inside a fibril, okay, dimension of a lamella, micelle, okay, intermicellar domain or interlamellar domain, the lamellar stacking, Okay, the configuration of the molecule, molecular extent, molecular orientation, that also can be, you can be able to measure by using X-ray diffraction. So now again, the X-ray diffraction depends on the angle theta. Okay, so as I have mentioned, if you use a wider angle of theta, is ranging from 5 degree to 30 degree, that type of principle is called wide angle X-ray diffraction, WAXD, wide angle X-ray diffraction. The wide angle X-ray diffraction give you the information about the closure spacing, much closer spacing. And if you use a narrow angle X-ray diffraction, okay, narrow angle X-ray diffraction or small angle X-ray diffraction, that is SAXD, then the angle of theta will be ranging from 0.5 to 6 degree. Okay, then you can be able to measure the coarser feature, that is the dimension of 10 to 100 nanometer. Okay, so basically WAXD and SAXD, okay, these two are different principle and the instrumentations are different. Okay, in the same instrument you cannot be able to go for wide angle diffraction or small angle diffraction. Okay, there are separate instrument. Okay, in the separate instrument the scanning degree, okay, so that will be different. In case of WAXD instrument, the scanning of angle will be ranging from 5 to 30 degree generally, and in case of small angle X-ray diffraction, the angle range will be 0.5 to 6 degree, and the purpose or the information which can be availed by these two instruments also will be different. Okay, in general, from the wide angle X-ray diffraction technique, we can be able to measure the molecular orientation in the crystalline phase, crystallinity percentage, and crystal size, okay, which are present inside the fiber structure. However, in case of narrow angle X-ray diffraction, we can be able to measure the coarse features, okay, such as long range order, molecular defects, okay, is there any periods of defects available, okay, so that can be measured by the small angle X-ray diffraction. So this is the schematic diagram of the instrumentation setup of the X-ray diffraction instrument. So you need not to go through in detail about the instrumentation. When you will be in the laboratory class, you may see the different parts. But only in this subject, we need to understand the principle of the measurement. Okay, just outline of the various part of the instruments and what are the results that can be obtained from the instrument, and most importantly the interpretation of the result. That is important to understand, interpretation of the result. So I shall go quickly in the interpretation of the result. Before that, okay, there are various parts of the instrument I just like to mention. That is the X-ray tube, okay, which will generate the X-ray radiation, okay, or the beam of X-ray, okay, that will incident on a sample. Sample will be placed on a sample holder. Okay, the sample holder is a movable type of attachment which can move, or which can move in this way that there will be the scanning of the X-ray beam over the sample with a 2 theta angle. So 2 theta angle is showing here. Okay, then there will be a detector. So detector will detect the reflected or diffracted X-ray from the sample, and which will go to the detector. So the detector will detect all the X-ray radiation, okay, which are coming to the sample, and the detector will produce a diffraction pattern, okay, diffraction pattern on a photographic film or in a camera. So the diffraction pattern which will be obtained by the X-ray diffraction instrument is very informative. Now we need to analyze the diffraction pattern. You need to know how to analyze the diffraction pattern. So if here you can see, this is the kind of molecular arrangement inside the fiber structure. Now this kind of molecular arrangement already you are familiar with, as you have gone through the various fine structure models. Okay, now if this is the scanning direction which is shown by the red lines, okay, here you can see there is a rigorous folding of molecule. As I mentioned, when there will be the folded configuration of the molecule, that zone is the crystalline phase. Okay, so if this is a crystalline phase, so that will give you a diffraction spectra in the ring. In the reflection spectra is like the concentric rings. Okay, that you already know, or you have also did some experiment in your physics laboratory also with the diffraction spectra of different polymers. So diffraction spectra is typically will look like in this way, either in a photographic plate or in some camera. So there will be the bright rings. Okay, there will be the central uh, maxima, and then there will be the numbers of rings. Okay, bright rings. Okay, there will be the bright rings. So the number of bright rings and the brightness and the width of the ring, that will depend on the type of the material which is used and type of the samples. Type of the material which is used for the measurement and type of the sample. Okay, sample or sampling, you can say. There are two types of sampling used for the measurement of textile and polymeric material. So one is powder sample, another is fiber sample. In case of powder sample, the fibers which are having a length or hair-like structure that are actually cut into small pieces, okay, by with the help of scissors, so that the powder particle is having a size in between 0.1 to 40 millimeter in diameter, and then those powders are compressed to form a pellet. Pellet is just a button like configuration. Okay, that pellet you need to form with the help of some salt. The crystallites are randomly oriented inside the pellets as a result. Okay, when you are cutting the fiber in like a powder and you are forming a pellet, the all crystallites which are present inside the powder particle, they are randomly oriented in all directions. Okay, and the diffraction maximum is obtained in the form of uniform circles. Okay, if you are using powder sample, then you will see the circles, the diffraction maxima or the bright lines are as circles. Okay, not like arcs. Here you can see this is not a circle, this is like arc. Okay, here one small arc, a bright arc is showing here, and another arc is showing here clearly, and in that place there are darkness. Okay, so but in case of powder sample, you will see concentric arcs only. That is, I will show in the next slide how the arcs and how the circles are appear. But when if you are using fiber sample, okay, when the fibers are held mutually parallel and straightened along their fiber axis in a bunch, owing to orientation of crystallites, diffraction maxima appears as arcs. Okay, so here in case of fiber sample, there is a sample holder, typical sample holder is available where you need to wrap the filament or fiber, or you need to place the fibers parallelly on the sample holder. Okay, either you need to wrap the fibers or filaments in the sample holder by placing the fibers of the filament parallelly. Okay, here no cutting is required. Okay, so as a result, the molecular orientation of the fiber, okay, that is not disturbed. Okay, in case of powder sample, as soon as you are cutting the fiber, the molecular orientation has been disturbed. Okay, so the powder sample is solely used for measurement of crystallinity of the fiber. But in case of molecular orientation, measurement of molecular orientation of fiber, you need to go for the fiber sample. Okay, okay, where you need not to cut the fiber, you need to place the fiber on the sample holder by placing the fibers or the filament parallelly. Okay, mutually parallel. Okay, so in case of fiber sample, you will get the diffraction spectra of concentric arcs, not circles. Whereas in case of powder sample, you will get the diffraction spectra of concentric circles, because in the powder sample, all the crystallites are randomly oriented in all directions. So that's why you will receive the diffraction spectra of concentric circles or bright rings. Okay. Now, after obtaining the diffraction spectra for the measurement of crystallinity, you need to go for radial scanning of powder sample for calculation of crystallinity and crystal size. Radial scanning, what is that? You can see this white line. Okay, this is the line of radial scanning. From the central maxima, if you go for measurement of intensity, okay, of the R in the radial direction, that is the radial scanning. From the center, you need to go for the measurement of intensity of the arcs in the radial direction, that is the radial scanning. Okay, so in the radial scanning, a graph will obtain, that is intensity versus 2 theta degree. Okay, 2 theta is coming from the Bragg's law. Now intensity versus 2 theta curve will be like this. Okay, this type of peaks will be obtained. As many as number of concentric circles will be there, bright circles will be there, as many as number of peaks will be obtained. Here you can see 1, 2, 3, 4. 4 prominent intensity peaks are obtained. So that means there were 4 concentric circles which are there in the diffraction spectra. Okay, because the intensity were high. So that's why you are getting intensity peaks. Okay, now those intensity peaks is actually representing the crystalline phase of the fiber. That is, you need to understand the intensity peaks wherever there is the brightness or bright arcs or higher intensity lines. These are formed due to the crystallinity or presence of crystal inside the fiber structure, because the crystalline phase only responsible for constructive interference of the X-ray beam for the production of bright lines, okay, or the maxima. So that's why you are obtaining the bright spectra, bright lines. Okay, so now if one can segregate those peak area to the diffuse area, that's just I am showing here by this line. The peak area is segregated by this blue line. Okay, the total peak area is measured by some software. Even you can use some paper and drawing the plotting the graph on the graph paper and counting the number of cells which are present in those comprising those crystalline peak. You can be able to measure the AC, which is the area due to crystalline phase, and the AA, which is the area due to the amorphous phase. Okay, the diffuse area, that is the AA. So percentage crystallinity can be then obtained by using simple calculation, AC divided by AA plus AC, where AC is the area due to the crystalline phase and AA is the area due to the amorphous phase. So AC and AA can be obtained by this method, and nowadays all these calculations are inbuilt in the software of the instrument, and you can get directly the values of crystallinity from the instrument itself. So this is the principle of measurement of degree of crystallinity in percentage, okay, by using the X-ray diffraction method with the powder sample. Now come to the fiber sample. In case of fiber sample, okay, you will not get the concentric circles. You will get only the concentric arcs. Okay, just as shown here in this figure. This is the arc. One arc is here in this position, another arc is here in this position. Okay, now for measuring the molecular orientation, you need to go for the azimuthal scanning. Okay, so I shall discuss later the azimuthal scanning. Before that, I want to discuss the determination of crystal size or crystal thickness. Okay, that is defined as T equal to K lambda by B cos theta, where K is a constant, and in most of the textile polymer, the value of K is close to 0.9. You can use this value for the calculation. Lambda is the wavelength of the radiation, that is the wavelength of the X-ray. Then B is the half width of the diffraction peak. Okay, because the crystal were present in various layers. Okay, various layers in the fiber. Okay, now due to those layers, there will be many peaks. Now, if you want to measure the crystal size at this peak position, then you need to measure the half width. Okay, this is the B, the width of the diffraction peak at the half of the intensity. Okay, if this is the full intensity, at the half of the intensity of this peak, the measured width of the peak is actually the B. Okay, that is the half width of the diffraction peak. B cos theta is the same meaning, the diffraction angle. Okay, so now from this equation you can be able to measure the thickness of the crystal or crystal size. The unit of the thickness will be the same as of the unit of the wavelength lambda. Okay, now come to the determination of molecular orientation. Okay, now azimuthal scanning is required. Azimuthal scanning is the scanning in angle. Okay, the azimuthal angle psi is showing here. Okay, if this is the arc, if this arc is represented here in this way, here you can see this. If this is the arc, bright arc, if this is the center, okay, then you can scan the intensity of the arc in azimuthal direction or psi angular direction. Okay, so now at the center of this arc, the brightness is maximum. You can see a higher intensity P, and deviating from the center point, the intensity gradually decreases. So as a result, the intensity curve gradually becoming smaller. So now in this way you can go for the scanning for all positions or all points of the arc, and after that there will be a averaging out of all intensity curve. Okay, there is a approach, okay, of averaging. There is an approach which is called Hermann's orientation function. Hermann's is the name of the researcher who have proposed this approach for measuring the molecular orientation of fibers in crystalline phase by some quantitative calculations. Okay, he has presented the orientation function as Fc, which is defined as Fc equal to 1 minus 3 by 2 average of sine square phi. Okay, now this phi is having the similar meaning of that is the diffraction angle theta. Okay, now this function Fc can be able to determine quantitatively the molecular orientation of textile fiber. Okay, now the numerical or mathematical expression of sine square phi is presented here in this equation. You need not to mark up this equation. Okay, but there is a derivation, but that is out of the scope of the syllabus. You need not to understand that at present. Now the angle phi has the same significance as the azimuthal angle psi. For perfect orientation, for the perfect molecular orientation, the value of Fc will be equal to 1, and for the perfectly random molecular orientation, the value of the Fc will be equal to 0. So the value of the Fc is actually ranging from 0 to 1. When the value of Fc will be come to 0, then the fiber is having the random orientation. And if the value of Fc is approaching towards 1, then you can interpret the fiber is having a higher molecular orientation. Now, by putting this value of Fc equal to 0 and 1 in this equation, you can be able to calculate the value of theta. Okay, So that the value of the theta will give you the idea about the average angle between the fiber axis and the molecular axis. Okay, that is the concept of molecular orientation as I have discussed earlier. So it is the task to each and every student to calculate the value of theta by putting the value of x equal to 0 and again by putting the value of x equal to 1, so that you can be able to understand what should be the value of orientation angle theta, so that the value of fc will be equal to 1 or will be equal to 0. So that concept will be used later on for understanding the various concept of physical structure of fiber. Now I shall show you some of the diffraction spectra of common textile fibers. So in the A you can see the diffraction spectra obtained for a regenerated protein fiber RDIL. Okay, you can see in this case the spectra, the lines are not prominent. That means the fiber is not highly crystalline fiber. So this fiber is actually highly amorphous fiber. So the wool, the second one, you can see the diffraction spectra of wool. So here the lines are not prominent. Okay, the circles are not prominent. So that means the wool is not a high crystalline fiber. As you know, the wool is having only 35% crystallinity. The silk, which is a highly crystalline fiber, you can see the bright spectra are there, as well as the lines are not concentric circles. Okay, they are only the arcs which are present. That means the silk is having a good molecular orientation. Hemp, okay, the bright arcs are converted, sorry, but bright lines or circles are converted into the arcs only. Okay, there are small dots, okay, or bright arcs. Okay, so that means the hemp, which is a bast fiber which is having a good molecular orientation and high crystallinity. So here in case of regenerated cellulose again, so fortisan, that is another regenerated cellulosic fiber, you can see there are bright arcs only. The bright circles are not present. Bright arcs are present. So that means this is a highly oriented fiber. So in case of high tenacity viscose rayon, even the bright arcs are present. That gives you the information about the high molecular orientation. In case of standard viscose rayon, arcs are not there, arcs are not present, rings are present. So that means the viscose rayons is having poor, standard viscose rayons having poor molecular orientation. In case of cotton, the arcs are there, so cotton is having the good molecular orientation. So in this way, you can interpret about the molecular orientation of various common textile fiber by observing simply the diffraction spectra. But for the quantitative measurement, you can, if you want to measure quantitatively the molecular orientation of those fiber, you need to go for the azimuthal scanning and use the Hermann's orientation function to calculate the value of the FC. Okay, then only you can be able to explain the molecular orientation of all these fibers. Okay, so because all these fibers are actually the measured in fiber sample, not powder sample. Okay, so you cannot be able to comment on the crystallinity percentage, because in case of powder sample only we can be able to measure the crystalline percentage. So now in case of mercerized cotton, you can see the smaller arcs are there. So another point I need to mention here, the smaller will be the arc length, higher will be the molecular orientation. Inversely proportional. Smaller will be the arc length, higher will be the molecular orientation. That I forget to mention, because if the arc length will be smaller, the theta, angle theta or azimuthal angle psi, that will be smaller. So smaller will be the angle, higher will be the molecular orientation. Okay, so that's why the arc length, if the arc length will be small, then molecular orientation will be high. So here in case of asbestos fiber, you can see the diffraction spectra of the asbestos. Okay, where you can see the arcs which are converted into dots only. There are only few dots. Okay, that means the asbestos is highly oriented fiber. Okay, because the smallest arc, that is the dots which are appeared in the diffraction spectra. Okay, so asbestos is having the highest molecular orientation among all those fibers which are presented in this slide. Okay, you can see the molecular orientation of acetate and nylon. If you want to compare, you can see the molecular orientation is better in case of nylon because the arc length is smaller than that of the acetate fibers. Okay, in case of glass fiber, you can see there is no arc. Okay, only central brightness is visible, but there is no bright arc is observed in case of glass fiber because glass fiber is highly amorphous fiber. Okay, so in this way one can interpret the molecular orientation of the fiber by observing the diffraction spectra of fiber sample. Okay, thank you, happy learning.